Hello all, welcome to the module. In the last module, we discussed about a simplest way of converting resistance to voltage. The reason why we have converted the resistance to voltage, as the next stage can accept only the voltage, any form of a signal has to be converted into the voltage so that the next stage can easy to process it. Then we have considered different sensors. So, since we have seen about the discussion about a sensor where the output of a sensor can be of any form, it can be voltage, resistance, current, or impedance change, resistance change, or a capacitance change. So, we discuss the ways of converting a resistance to voltage. But what we have seen, using a resistance, a simplest resistance to voltage conversion circuit will provide an offset. Though it converts a resistance to voltage, it provides an initial offset when we are designing it, right. And we have also seen how to eliminate an offset, what is the use of different subsystems, what is the role of signal conditioning circuit, what different properties that each subsystem should have, so that no loss of the signal from the sensor to the acquisition side. And we have also designed the circuit to eliminate the offset, to amplify it, and different ways of designing that using different operational amplifier configurations. So, in this we will see another way of converting a resistance to voltage by using a Wheatstone's bridge circuit. So, the advantage of Wheatstone's bridge circuit is, instead of using a one pair of a resistive divider network, it uses a two pairs of a resistive divider networks, but the output voltage will be difference between these two, right. So, that we will see how can be used, how a Wheatstone's bridge circuit has to be designed in order to convert this resistance to voltage. What is the advantage of using Wheatstone's bridge circuit when compared to resistive divider network? We will see in today's session. So, Wheatstone's bridge circuit uses 4 different resistors which can be helps to identify the unknown resistance available. So, when you look into the Wheatstone's bridge circuit, as here you can see, it contains, if you look into the left side as well as the right side contains one resistive divider network, whereas the right side also contains another resistive divider network. The output voltage is nothing but the difference between the first resistive divider network configuration to the second resistive divider network configuration. What I mean in the sense, imagine say the previous circuit whatever we have, which is at 10 volts, which is R1, which is 1K if I imagine, or this is also R1 base resistance. The output we know, the output whatever we measure is with respect to the ground, right. So, this will be, if both the resistance are same, then it is V in by 2, which is 5 volts. This is a resistive divider, but whereas the Wheatstone's bridge, it uses two pairs of a resistive divider network. So, but whereas in this case this is an unknown resistance which we have to find out, whereas in this case both the resistances are fixed. So, this is also 10 volts, the same voltage that we are using here, it will be always V in by 2, but here the output voltage depends upon R1, the sensor, but whereas in this case since both resistance are fixed, so it is V in by 2. Now, this output voltage whatever we measure is also with respect to the ground. When we take the difference between the first output, the output from the first pair of resistive divider network to the second resistive divider network, then that is nothing but your Wheatstone's bridge circuit. So, the V naught is nothing but, if I say this is VO1 and this is VO2, VO1 minus VO2. But what is the advantage of going with the Wheatstone's bridge circuit? One is, since we are measuring the difference between the two terminals, and the selection of a resistance will provide an output voltage to not to have any offset, right. It starts from, see, if what I mean in the sense, if you consider all the 4 resistance equivalent or all the other 3 resistance is same as the base resistance of the sensor under no loading condition, the output voltage will be always starts from 0. So, the effect due to that we have seen in the resistive divider network in the previous case, where it always gives an offset of V in by 2 or half of your input voltage, by using another pair of resistive divider network and differencing the output voltages will compensate for the offset created by the resistive divider circuit alone. right. So, this is the advantage of going with resistive Wheatstone split circuit. And another advantage is, so when we have two different sensors, one with R plus delta R, right, other one with R minus delta R configuration, or with the same R plus delta R. Suppose say this is also another sensor which is R plus delta R, but it is only for measuring the temperature, but the change that we get. So, this is R plus delta RT, but whereas this is R plus delta R, which is based on the changes with respect to the physical measurement, but whereas this is for the temperature compensation. Since both the sensor materials of the same type, this introducing another sensor into the second pair of resistive divided network topology can compensate for the temperature losses, temperature effects. First stage of temperature effects can be completely compensated using this. This is another advantage of it. But the problem is utilizing a single varying element. Here if you can see, using a single element varying element in a Wheatstone split configuration introduces a nonlinearity error. What I mean by nonlinearity error? So, imagine if I have output voltage, if I see the characteristics between V0 and V in as this linear, but because of only single varying element bridge in the Wheatstone split circuit, it leads to some kind of a nonlinearity. This nonlinearity error, when you consider, it will be always 0.5% by percent. What I mean? I can simply show you one simple example. Imagine say I take R as 100 ohms, 100 ohms, 100 ohms and 100 ohms. So, whereas this is a sensor, this is a sensor. So, 100 is the base resistance of the sensor. So, in order to compensate or in order to avoid the offset, so all the resistance have been designed in such a way that the value of the base resistance is selected. So, now under no loading condition where R is equal to 100 ohms, the V0 is equal to here VB by 2, here also VB by 2. So, which is become 0. So, when do you say there is no nonlinearity? So, in order to say the system does not have a nonlinearity, two different conditions have to satisfy. One is superposition, other one is a scaling. So, any one of the problem does not satisfy, any one of these two theories does not satisfy, then the system is said to be a nonlinear. So, first consider a scaling factor. What it is? If y is equal to kx, right? If the k is a constant throughout the operation of a y or x, then the system is said to be completely it satisfies the scaling factor. So, the value of k should be always constant. What I mean? Imagine say if the k is a 0.5, for input of 1 y should be 0.5, input of 2 y should be 1. But if I say for input of y the scaling factor as 0.5, if input of 1 if the scaling factor of 0.5, and if input of 2 if the scaling factor is not 0.5 and if it is changing, right, it is varying with respect to the input, then it is not satisfying the principle of a scaling, which means that it is not a nonlinear. That can simply understood because the k should be constant. So, that means y should be always proportional to x. Now, by observing this, if this particular theory does not satisfy, we can simply say the system is a nonlinear. So, now consider it. So, now what happens when all under no loading condition and all the resistance are same, V0 is 0, good. Then say for any change of resistance, because this is only the sensor, for any 10% change of a resistance, if I observe the output variation is some y%, if that y% is constant throughout the operation, I can say this is linear. Now, say for 100 ohms into 10%, so 10% will be 10 ohms. These are sensor 100 ohms, 100 ohms, 100, 100. So, both are connected with VB, which is 10 volts. Now, this is VO1 I am considering and this is VO2. So, V0 is nothing but VO1 minus VO2. We are observing about the scaling. Now, say if this is increased by 10%, what should be V0? Now, VO1 is equal to, since the resistance are same, it is 5 volts VB by 2 minus, whereas VO2 is 10 into 110 divided by 100 plus 110. So, 210. Solving for this, we get minus 0.238, right. So, this negative, because since we are measuring between VO1 and VO2, it is a negative. If we measure between VO2 and VO1, then this will be positive. So, now we got 0.238. Imagine now, if the change is of 20%, if the output change is also doubled, then I can say linear. Now, if I consider this value, case 2, now the change is 20%. V naught is equal to VO 5 minus 10 into 120 divided by 220. Now, this is minus 0.4545. Now, see, when I am dividing 0.4545 by 2, half, because the change is also half, here in this case double, from 20 to 10%, its changes of half. Now, if you see, the change is not exactly half. Now, consider, say if the change is 30%. So, that means V naught is equal to 5 minus 10 into 130 divided by 230, minus 0.652. So, calculating 0.238 into 3 times, the value 0.283 into 3, we get 0.714, but increasing by 30%, which is 3 times higher than the original one, I should get 0.714, but now I am not getting 0.74. It is only 0.652. Even doubling is also the same. So, which means that, so when you see for change of 10% as an input, the change is not, the scaling factor is not the constant for the output. So, which means that y is not proportional to x anymore. So, there is a slight deviation. That deviation is because of the delta r by 4, which is acting in the denominator, r plus delta r by 4, right. This r plus delta r by 4 causes the output to have non-linear. So, that is why a single element varying bridges, not only it has an advantage of removing, compensating for the offset voltage, but it introduces a non-linearity error into the system. At the same time, it cannot even compensate for the temperature effects or temperature changes. But how to solve this? One way is using 2 element or 4 element varying bridges. So, you have another topology here, 2 element varying bridges too. So, these 2 element varying bridges, where if you have the same type of resistance change, when you consider the same type of a resistance change and adding in this way, why we should not add here, why we should not add here, why it should be always added in this configuration? Because when we add here, if both are changing at the same rate, the output voltage that we observe will remain same, it will not change, even though the sensor is changing with respect to the load, right. When we are having the same resistance change, the effect will never be seen. So, that is the reason for a temperature compensation, if the sensor we are using is only for the temperature compensation, adding a resistor at this point always advantage, provided that sensor should not change with respect to the input load, input parameter or input measurement, it should only compensate for the temperature effect. Imagine, say if you want to amplify, if you want to eliminate the offset, and if you want to amplify the output voltage. See here, if you see, it is attenuating VB by 4. Even in this case, of course, it is amplifying by twice that of the previous circuit by utilizing 2 different same type of a sensor, which can measure the same physical measurement, not for the temperature compensation, for the physical measurement, same physical measurement. It cannot avoid the nonlinearity error, but it can amplify your signal when compared to the single element varying bridges. But another topology what we have is, if we have one as a positive resistance change, another one as a negative resistance change. So, which means R plus delta R, R minus delta R. The base resistance will remain same, but one is a PTC, other one is a NTC. So, for a same X load, if the change is of Y. But whereas in the first case, if it is adding with respect to the base resistance, whereas in the second sensor it is subtracting from the base resistance, then it is said to be R plus delta R and R minus delta R, and nothing but one is PTC, other one is NTC. If such kind of a sensors are available, introducing into the one pair of a resistive divider network not only avoids a complete nonlinearity error, it compensates for the resistance temperature effects, it also amplifies your output when compared to the single element varying bridges. But having one with a PTC and another one with NTC is very difficult, which cannot be happen in all the cases, right. Another thing is 4 element varying bridges, where in the case of 4 element varying bridges, see, the selection and the placement of sensor should be as follows. Any change of the position again leads to no change in the output voltage, even though the change if input measurement is being changed. So if this is R plus delta R, this should be R minus delta R. If this is R minus delta R, this should be R plus delta R, and this is R minus delta R. Placing in this configuration avoids a complete nonlinearity error. Nonlinearity error is 0 and the output voltage is VB. So no attenuation involved into this. So in this case, V naught is directly proportional to delta R. So VB by R is the factor, which is a K, proportionality constant K, right. So when you use a load cell, where they uses a strain gauges, 2 strain gauges will fix on the top and 2 strain gauges will fix on the bottom on a cantilever, and when a cantilever, so imagine, say if this is a cantilever structure, and if you want to see the application of all element varying bridges, if I use 2 different sensors on the top and 2 different sensors on the bottom and applying a force on this, these 2 sensors will experience R plus delta R, and whereas these 2 sensors which are attached on the bottom side of the cantilever will experience R minus delta R. So one R plus delta R placing it here, another R minus delta R placing it here. Similarly, R plus delta R minus delta R, the V naught we will get as delta R. The output voltage is directly proportional to delta R. Remember that this nonlinearity error is not because of the sensor, it is purely because of the signal conditioning circuit that we have designed. So that is the reason the proper designing of a signal conditioning circuit is also important to solve, to provide a linear output, accurate output with very good information about the input too, right. One is nonlinearity error is solved. At the same time, since we are utilizing all 4 resistance, all 4 varying resistance are varying, any effect due to the temperature will also be compensated, right, because if the change in the resistance is due to the temperature, where delta R now is because of delta RT, now all the element, if this is a strain gauge, all the resistance will have change with respect to positive change with respect to resistance. So that means all resistors will behave as R plus delta R for case of a temperature change. So when all resistance are delta R plus delta R, the V naught will be VB by 2, here also VB by 2, so V naught is equal to V naught is equal to 0. So it compensates for the temperature effects. At the same time, if any physical measurement change when the force is applied, right, the output voltage will be linear. This is how the 4 element varying bridges utilizing Wheatstone switch configuration works. Of course, in all the cases you cannot achieve the same type of you cannot get all 4 combinations, all 2 combinations of resistance. If it gets, we can introduce it, but what if we do not get all combinations of resistors here, one with a PTC, other one with NTC, right, then we have to optimize our design in a similar fashion. So instead of using a voltage, we can go with a simple current. When we go with a constant current as an input in terms of voltage, here we can see V naught is proportional to delta R, and with a proportionality constant of IB by 2, even when you have R plus delta R and R plus delta R as your sensors too, right. This is another way of designing, another modality of designing a signal conditioning circuit with the same element varying bridges, instead of using voltage as an input, using as a constant current. Producing a constant current, again it is a problem. We have to look into that. Right. Now, how do we measure this output voltage? Of course, we have measured, of course, we know how to utilize, but if we want to give it as an input to the ADC, where ADC does not have a differential output, a differential input, ADC cannot measure a differential input. So, remember that the output voltage that we get from a resistive divider network is with reference to the ground, whereas the output from the Wheatstone split circuit is a differential output. So, which means that you should always measure one voltage with respect to the ground, with respect to the another voltage with respect to the ground. The difference between these two voltages is nothing but V naught. It is not with respect to the ground. So, in such cases, we cannot use either an inverting amplifier configuration or a non-inverting amplifier configuration, because the inverting amplifier or non-inverting amplifier configurations can only be amplified or attenuated with for a single input voltage or with reference to the ground, but whereas in this case a differential. So, for that the general procedure is using a difference amplifier, differential amplifier or difference amplifier. But again, when you look into the difference amplifier, this is V1, this is V2, this is output R. If I say this is R1, R2, R2, so V naught is equal to R2 by R1 into V2 minus V1. So, V naught can measure the difference between V2 and V1, and if R2 and R1 are same, then the gain is 1. So, output voltage is purely difference between V2 and V1. But because of this R1 input resistance, right, the input impedance of the system entirely depends upon R1, and in this case, since the output from the previous stage is not directly connected to the input terminals of an operational amplifier, the loading, the chances of having a loading in this case is higher because of the input resistance value. Selection of input resistance is also very much important, right. Of course, there are other ways of doing it which can avoid the effect due to input resistance, that is instrumentational amplifier, 3 op amp based instrumentational amplifier, where even though it uses a differential amplifier inside 3 op amp based instrumentational amplifier, because of the topology or the configuration of 3 operational amplifier, the input impedance is of very higher. At the same time, the CMRR, which is a common mode rejection ratio, the ability of the system that can measure the common signals, the same signals, is also high. So, this is a difference amplifier. So, as we discussed, in order to meet the properties of the next subsystem, the difference amplifier input impedance of the next stage should be always higher, so that no current will be drawn from the preceding stage. So, in order to have a very high input impedance by utilizing on operational amplifiers, if we connect the output from the preceding stage directly to the input terminals of an operational amplifier, it will have a very high input impedance, so that no current will be taken from the previous stage, which means that from the sensor side. Otherwise, the current drawn from the previous stage entirely depends upon the input impedance that you have selected or that we have designed. So, that is one disadvantage of going with a difference amplifier, because as we discussed, the difference amplifier will have an input resistances both on the negative terminal side as well as an positive terminal. In between the output from the previous stage to the direct input to the inverting or non-inverting terminal, it always contains an input resistance. Because of that resistance, the complete input impedance is decreased because of that input resistance values, right. And moreover, a difference amplifier will always have a very poor CMRR, which is nothing but a common mode rejection ratio, the ability of the system to measure the common signals. So, one way to avoid that problem is by using an instrumentational amplifier, right. So, though this approach helps us to measure the difference between these two terminals, it cannot cannot compensate on the nonlinearity that we have discussed previously, which is delta R by R. In order to avoid this nonlinearity, either we have to go with the two element varying bridges, as we have seen, we have to use some other topology to eliminate the nonlinearity. So, are there any ways to use a single element varying sensor utilizing a circuit so that the output should directly proportional to the resistance? Of course, a modified version of a Wheatstone's bridge circuit. It looks like a Wheatstone's bridge circuit. In reality, it is not. It is similar to a inverting amplifier configuration, but it has an offset which is connected at this terminal. So, utilizing this configuration, the output voltage we can achieve as a directly proportional to delta R. That proportionality constant here is Vb by 2R. Vb is nothing but the input voltage that we have connected to the complete system, and whereas R is nothing but the base resistance, right. So, how does it work? As we have already seen about the working of an inverting amplifier configuration. So, if you see this, I am retrying in a different way so that it is easy for us to understand the circuit. R, and this is R plus delta R. R plus delta R represents the sensor. Here we have an offset. That offset is created by this. So, since R and R are having same resistance value, then this particular voltage is nothing but Vb by 2. So, we are applying a fixed voltage at the non-inverting terminal, which is Vb by 2. What we have seen in the previous discussion, this Vb by 2 will subtracted will be added to the output voltage. How? So, we know that V naught is nothing but R plus delta R divided by R into, say, if this is VO1. So, this terminal as VO1, it is nothing but VO1 minus and plus 1 plus R plus delta R by R into Vb by 2. So, this is the equation, this is the output that we get. Solving for everything, we get V out is nothing but V out is directly proportional to delta R. So, how this particular configuration is making an output to be linear? So, how in the sense? Since this sensor is connected in the negative feedback topology, as we already aware, this I1 will be always equal to IF, right. So, this particular potential will be varied, depends upon the varied in order to maintain the same current to flow between same current to flow in the resistance R as well as R plus delta R. So, which means that the current flowing through R plus delta R will be a constant throughout the operation. So, what is going to happen? Any change in the sensor resistance, since the I is already constant, it changes the output voltage, because of which we get output voltage proportional. You can further solve about this. So, I1 is equal to IF, this is the basic rule which we already know, VO1 minus Vb by 2 divided by R is equal to Vb by 2 minus V naught divided by R plus delta R. So, just for easy understanding, I am saying R plus delta R as Rf. So, now we can see VO1 by R is equal to Vb by 2 R plus Vb by 2f minus V naught. Taking V naught in this direction, V1 by R in this direction. So, this is V naught by Rf. So, we get V naught by Rf is nothing but Vb by 2 into 1 by R plus 1 by Rf minus VO1 by R. So, solving for that. So, V naught is nothing but Vb by 2 into 1 plus Rf by R minus VO1 into Rf by R. So, this is what we have seen previously. The simplest way to understand the circuit is you can use a superposition principle too. So, in the superposition principle, since you have a 2 voltage, making 1 voltage connected to the ground, other making only 1 voltage available. So if this looks like a non-inverting amplifier configuration, if it is a non-inverting amplifier configuration, V0 is nothing but 1 plus RF by R into VO1 into VB by 2. So this is what we have seen, VB by 2 into 1 plus RF by R. So in another case, VB by 2 will be ground, and then it looks like a non-inverting amplifier configuration. So during the inverting amplifier configuration, it is minus VO1 into RF by R1. So RF by R. This is what we have seen in the previous equation. Now solving for this, so imagine say if RF, so what is VO1? This is not VO1, so this is VB. This is VB, right? Now taking VB as common, VB by 2 plus VB by 2 into RF by R minus VB into RF by R, right, which is equal to VB by 2 plus RF by R. If I take a common, VB into RF by R, so 1 by 2 minus 1, which is minus 0.5. So I can write it down as this as VB by 2 minus VB into RF by 2R. So what is RF? We know RF is nothing but R plus delta R by 2R. So splitting it, VB into R by 2R, RR cancel, minus VB into delta R by 2R. So this cancel. Now V0 is nothing but VB by 2R into delta R. So that means VB is directly proportional to delta R, but we always get a phase shift minus. Of course, we can use another inverting amplifier configuration in order to remove the phase shift, which can also help us to amplify the signal as well as to remove the phase shift that it is that we are getting from the previous stage. But in this configuration, by using a single element resistance, we can convert the resistance to a linear output voltage. This is another way of designing a signal conditioning circuit, another approach of signal conditioning circuit by using a single element varying a bridge to get a linear output. I hope this is clear. Now we will see another practical application where in the next class we will use the similar application, interface it to a data acquisition device, and we will display the temperature of the sensor on the screen using data acquisition module and lab. So in order to do that, I will consider a simple example. So this is a problem of a signal conditioning circuit that I am considering to show it to you tomorrow. So because of since we are directly interfacing to the system, we should understand what exactly the problem is. So the idea is that we want to display the temperature of a system, or temperature of a boiler, or temperature of room temperature. So in order to do that, since temperature and data acquisition device accepts only a voltage as an input, the temperature has to be converted into an voltage. So in order to do the conversion, we use a transducer, an input transducer, which is nothing but a sensor. So in this case, since there are different varieties of sensors which uses a different physical phenomena to convert the temperature to output. So in this particular example, I am considering LM35. LM35 is a semiconductor based temperature sensor where it gives an output in terms of voltages, right, in terms of voltage. So when you look into the data sheet of LM35, here we can understand the data sheet shows that the sensitivity of LM35, the temperature sensor which is easily available in the market, is 10 millivolt per degree centigrade. What does it mean? Every change in 1 degree centigrade, it changes the output voltage by 10 millivolt. So that means 1 degree centigrade will be changed by 10 millivolt. If that doesn't have any offset, so this will be the starting. So that means 0 degree will be shown as 0 millivolt, whereas 1 degree centigrade will be shown as 10 millivolt. Any change in a degree will correspondingly the output voltage will also change. Now, what is the operating range? The range at which it can be operated is minus 75 degrees centigrade to 150 degrees centigrade. Since the idea of using this temperature sensor is to measure the room temperature, right, and the linearity is also very good. So, considering all this factor, this particular temperature sensor we have selected. Now, how do we design and what is the need of a signal conditioning circuit here? Since we are planning to interface to a ADC, where in one of the data acquisition device DAQ has an ADC, inbuilt ADC, which is 8-bit ADC, let's say, directly connecting the output of sensor to ADC, it will not meet all the levels of ADC. So, that means though we can achieve a better accuracy as well as the resolution of the temperature, because of limited uses, because of improper signal conditioning circuit, we are unable to display with a very good resolution. So, the problem says here, design a signal conditioning circuit for LM35 to display the output temperature changes in human understandable values. What it means? It should represent in terms of degree centigrade, whereas the temperature sensor can only show in terms of millivolts. So, 1 degree centigrade should be represented with 0.1 volt, 10 degrees centigrade should be represented with 10 volts. This is the condition, right. The sensitivity of the LM35 is given as 10 millivolt per degree centigrade, and to change the sensitivity to 0.1 volt per degree centigrade, amplify the output. So, what it shows here, now when you look into the scaling factor, the scaling factor is 10 millivolt per degree centigrade is what given by the sensor. But what the problem says, we require to represent, in case if we are not using a data acquisition device and if you want to display using a voltmeter, measuring unit, voltmeter, where the voltage is corresponding to the temperature. So, that means 10 volt when you measure, it should it is an indicator that this is 100 degrees centigrade. If 0.1 volt is being measured, which means that it is an indication of 1 degree centigrade. How do we design a signal conditioning in such a case? So, which means that when you look into that, 1 degree should be represented with a 0.1 volt, right. So, which means that now 1 degree is represented with 10 millivolt. So, in order to match the scaling factor of what we require and what is already existing, we require to multiply a gain of 10. So, if I multiply a gain of 10 to the output of temperature sensor, so which means that 100 millivolt will be represented for 1 degree change, which is nothing but 0.1 volt per degree centigrade, which is matching with respect to what we require. Now, how do we design a signal conditioning circuit to have a gain of 10, right? Now, one thing what we have to understand, what kind of output that temperature sensor is giving. It is directly voltage. Since it is an output voltage, we do not have to think about conversion of a resistance to voltage, right. We can directly use it. Then second thing, what we have to think about, loading effect. Since we are interfacing it to another stage, there should not have loading effect. If there is a loading effect, the previous stage, which is nothing but a temperature sensor, should have enough energy to operate it, right. So, since temperature sensors cannot provide enough energy, which means that current is also a part of energy, right. So, since it cannot provide enough power or enough energy, we have to have a limited current drawn from the previous stage. So, in order to do that, in order to create a gain of 10, one way is either we can use a simple inverting amplifier configuration, but since inverting amplifier configuration has an input impedance, in this case we are selecting to go with a non-inverting amplifier configuration, where the output from the previous stage can be directly connected to the input of a non-inverting amplifier configuration, non-inverting terminal, so that the input impedance is very high. So, no current will be taken from the previous stage, so from the temperature sensor. Now, how do we design with a gain of 10? Since we know the gain of non-inverting amplifier configuration is RF by R1, so and it is required to have a 10. If I design RF is equal to 9 times of R1, then the problem is solved. If I consider R1 as 1 kilo, RF to be of 9 kilo, but identifying a matching resistor is very hard. So, in this case, to have a gain with availability of the resistance in the market, we have considered R1 as 2.2 K, R2 as 20 K. So, which will become 1 plus 20 K divided by 2.2 K, which is close to 10. So, the value is 10.09. 0. So, which is close to 10. So, this can be used to convert 10 millivolt per degree centigrade to 0.1 volt, a simplest signal conditioning circuit. So, in the next session, we will use the same temperature sensor, right. Since the output is very small and ADC, in this case the reference voltage of an ADC is of 5 volts. Let me take empty slide. I will take temperature sensor output where the output is 10 millivolt per degree centigrade. This I will be directly interfacing to USB DAC with a gain of 1, which has an onboard ADC, and we use a LabVIEW software to display the temperature values. When the gain is 1, we will see what is the resolution that we are going to get. So, since USB DAC operates at 5 volts, temperature value 5 volts, and it has 8-bit ADC on board. So, this 5 volts will be divided into 2 power 8 number minus 1, which is 255 levels. So, that means when I say this is 5 volts, this 5 volts will be divided into 255 levels. Each level height will be 5 divided by 255, which is 19 millivolt, right, 19 millivolt. That means anything lesser than 19 millivolt will be always considered as 0. So, now if you imagine, if the change in the temperature is 1.5 degree centigrade, that means the actual output voltage will be only 15 millivolt. So, it is only 15 millivolt, but right, it falls under this particular level, which is starting level. So, 0 0 0 0 0 0 0 0, right. So, 19 millivolt will be always considered as 0 degree centigrade, even though the actual temperature is 1.5 degree, but the sensor, the display unit can only measure 0 degree. That is not because of improper selection of an ADC. I can say even by utilizing 8-bit ADC, by slightly changing the gain, by introducing a signal conditioning circuit between a temperature sensor and ADC with a gain, right, the output or the temperature can be displayed with a very high resolution, right. Imagine, say, in the same situation, if I have a gain of say 5, so that means now it will be 1 degree centigrade will be represented with 50 millivolt. Now, 1.5 degree is nothing but 50 into 1.5 millivolt, 75 millivolt. Now, this 75 will fall under which category? So, which means that if 50 millivolt is represented with 1 degree centigrade, then 19 millivolt will be 0.38 degree centigrade. So, the temperature can be measured with a resolution of 0.38 degree by introducing a gain amplifier, by introducing a signal conditioning circuit there. So, but utilizing the same 8-bit ADC, right. So, since theoretically we can show this, but practically as a temperature varying such a small temperatures are different, I will show you considering the same room temperature with a gain of 1, how the output voltage, how the temperature is being displayed in the LabVIEW, and the configuration, the interfacing thing will be discussed in the tomorrow session. Thank you.